Everyone. Thank you for joining us for today's Surface Measurement Systems online webinar. Today, we'll be exploring the topic of analysis of food products by dynamic vapor sorption. Today's session will be a live presentation with our very own Meishan Gao, followed by a live Q&A with Meishan as well. Meishan started working as an application engineer and is now an application scientist at Surface Measurement Systems. And since joining in 2018, she has been working on surface characterization of solid materials, including fiber, powder, and film samples, using dynamic vapor sorption and inverse gas chromatography as her primary techniques. Meishan obtained her master's degree in chemical engineering at Imperial College London in December 2017. Her research project was focused on investigating the properties of fragrance molecules with solid substrates by diffusion and sorption. She also received her bachelor's degree in chemical technology at the Hong Kong Polytechnic University and in chemistry at Sun Yat-sen University in June 2016. So without further ado, I would like to pass over to Meishan. But just before I do, I'd like to remind everyone of a few of the house rules for the session and how you can take part in the live Q&A. We ask everyone to keep their mic muted throughout the course of the live presentation, just to avoid any audio interruptions or background feedback noise that might ruin the audio quality for any of the other people listening. And we will, as mentioned, have a live Q&A at the end of today's session. This can be engaged in two ways. If you would like to submit your question in writing, you can do so in the questions tab on the webinar control panel. And then I will ask Meishan your question at the live Q&A section. Or alternatively, if you would like to unmute your microphone and ask the question yourself, if it's maybe a bit of a longer question or you need to provide any elaboration on it, you can raise your hand in the dashboard, and then I will let you know when you can unmute your microphone and you can ask the question yourself through your microphone. So once again, you can submit your questions in writing for me to ask, or you can raise your hand and I will let you know when you can ask the question yourself. So without further ado, I will now hand over to Meishan to begin today's presentation.
Thank you, John. Let me share my screen. So I hope all of you can see it now.
Yes, we can, Meishan.
Okay, that's great. So first, hello everyone, I'm Meishan, and welcome to today's webinar. In this presentation, I will just focusing on the food products, and let's talk about how the DVS technique can be applied in the food sample analysis. So here are some topics we will cover today. We will first have an introduction about the moisture sorption process. Then we will talk about the DVS technique, and we can go through some applications related to the shelf life or the stability studies of the food sample, including, for example, the isotherm determination, the vapor-induced phase change, the permeability measurement of some packaging material, as well as we can measure the water activity determination with our paint cell accessory as well. So moisture is everywhere in the real world, and the relative humidity can vary in different areas. So the interaction of the moisture with the solid material will have a great impact over a wide range of industries, including the pharmaceuticals, food, proteins, packaging material, also personal care products. And especially in the food industries, moisture will cause lots of different problems, like the powder caking that will affect the powder flowability in the final application, or the instability of the product, both physically or chemically. And the moisture-induced phase change, for example, like dissolution or the deliquescing of the sugar sample at higher humidity environment. So it's very important to study this kind of moisture sorption behavior for the prediction of the stability for the food products. And one of the popular properties we will measure, especially in the food industry, is the water activity, which measures how tightly the water molecule is bound to the solid material at certain temperature. So we can get this kind of information from the water sorption isotherms and also calculate some other property like the monolayer content, the heat of sorption, diffusion constant, or the permeability of the packaging materials. So there are some commercially water activity meters in the market which are simple and quick analysis, but it only measures the free water in the material, not the total moisture content. And a relatively large sample amount is also needed for the analysis with certain meters, like several grams of the sample. And of course, the experimental condition is not under control, so we cannot study the factors that will affect the water activity. So these are not suitable to measure the moisture transmission rate for the packaging material as well. Therefore, we are looking some other methods for the material characterization of this kind of moisture sorption for the food materials. So for the characterization of the solid material, generally we will have use energy as a probe, like the spectroscopy method, where we can get the analytical and structural information of the solid material. Or we can use heat as a probe, like the TGA method, to get some thermodynamic information of the solid. And in case of the dynamic vapor sorption technique, it's a sorption technique that we are using molecules as a probe, and based on the interaction of the probe molecule and the solid material, we can get all the property of the solid related to the structure, chemistry, as well as thermodynamics. So when we talk about a molecule interact with a solid, it will be either adsorbed on the surface of the material or absorbed into the bulk of the material. So by studying the kinetics of the sorption and the desorption, we can then easily predict some behavior of this solid sample in the bottom here at certain condition, at a certain temperature and relative humidity. And then we can calculate the property of this sample, for example, the BET surface area, the stability of the material, or the shelf life of this material at certain conditions. So when we talk about the molecules absorbed on the surface, it can be either by physico-chemical or chemical-chemical. So physico-chemical is a kind of weak interaction that the probe molecule are not chemically bonded on the surface, and it's more like a reversible process. And the property we can measure with the physico-chemical here is more like some property on the surface, for example, the surface area, the surface energy, pore size distribution, or heat of sorption. And another kind of stronger interaction is the chemisorption, that the probe molecule will form some covalent bond on the surface. And this kind of interaction is more for some special material, like you want to have a particular interaction with some probe molecule. And the property we can measure, for example, the active surface area or the catalyst dispersion. And in case of the absorption, it will be either by bulk sorption, that the probe molecule will penetrate the surface and then go to the bulk of the material. So in this case, the desorption is usually a diffusion limited process, and the kinetics of this bulk sorption will be much slower compared to the physisorption. So the property can be measured here, for example, the vapor-induced phase change, that we can get the glass transition temperature and humidity from the sample, or some other property like the total sorption capacity, the solubility parameter, or even the diffusion coefficient and the permeability for the thin film samples. The last kind of interaction is the absorption into the lattice structure, which means the material will change the structure in the presence of any kind of vapor, like water vapor or organic solvent. And this will lead to the formation of hydrate or solvate. So from the DBS data, we can study the structure of this hydrate as well as the kinetics information about its hydrate formation or dehydration. So we can get all those kind of interaction from different pro-molecule and solid interaction, and from the DVS experiment, we can calculate those kind of properties. And in case of the food industry, we usually use water as the molecule to measure different interaction between the water molecule and food material by the sorption and desorption isotherm from the DVS data. So DVS is for the dynamic vapor sorption, which is basically a gravimetric method that we can measure the change of mass for the sample at different concentrations of moisture or organic vapor. So we will base on ultra balance with the resolution of 0.1 microgram, and we just need to use very small amount of sample because this system has very good sensitivity, typically just around 10 to 20 milligram of the sample if the uptake of the sample is good. And as a dynamic system, we have a continuous flow of the pro-molecule to the sample, so we can achieve a much faster equilibrium compared to the static method. And all the experiment can be performed at ambient temperature and pressure. So it will be more close to the properties we will apply in the real world that is more, it simulates the real world conditions. So here is the schematic of one of our systems, the DVS resolution. This system can measure the sorption of water and organic vapor, as well as the competitive sorption of two different components. So in the middle of the system here, we have the macrobalance. It's connected to both the sample pan and the reference pan. We will then put the sample in the sample pan and keep the reference pan empty. And as you can see, there are two bottles at the back of the system. So one bottle is for water, the other bottle for the organic vapors. The carrier gas for the system could be nitrogen or dry air, and there were different mass flow controllers to control the flow of the carrier gas and the saturated vapor in ratio to reach a certain level of relative humidity or partial pressure. And this mixture will be detected by the sensor here, so the Rotronic probe for the water and our speed of sound sensor for the organic vapors. And we will make sure the actual generation of the vapor is matching with the target concentration. And this mixture will flow to both the sample chamber and the reference chamber at a constant rate. And the sample inside the chamber here will pick up the moisture, and the mass change will be recorded by the balance. So the whole stand, like this one, will be set in an incubator with the temperature range from 5 to 85 degrees. That means we can perform the experiment exactly from 5 to 85 degrees. But in some cases, we might need to precondition the sample at higher temperature, and in that case, we can install a preheater under the sample chamber at this location. And this will allow you to precondition the sample before the experiment in situ up to 200 degrees. And we can also combine the DVS system with some other accessory, for example, some camera also at this location to take the sample images at different humidity along with DVS data. So for example, here with some sucrose sample, at dry condition, the data image shows a powder form, and then it goes through the glass transition, crystallization at a higher point, and also the deliquescence, like go to the liquid form at high humidity. So this setup just with the video camera and the DVS gives us a good idea about how the sample will change the structure or change in the nature or change into different color along with the DVS data. And another option with the accessory is we can integrate the Raman spectroscopy with our DVS system, that we can take the Raman spectra at the end of each humidity step, And in that case, we can get both the Raman spectra and the DBS data at the same time. So for example, here the example is an amorphous lactose sample. We did the water sorption experiment at 25 degrees. So here the blue line indicates the partial pressure of each step. We increase from 0 to 95% RH with 10% steps. And the red line is the change of mass for the sample. So at each stage, the sample is picking up the moisture, it's reaching a perfect equilibrium, and then jump to the next stage automatically. But as you can see at 60% RH here, there is a significant decrease in the mass for the sample, and this is due to the amorphous to the crystalline phase change, because the crystalline state material has smaller surface area as well as less sorption capacity. And this kind of amorphous to the crystalline phase change is an irreversible phase change, as you cannot see the same effect in the second cycle here. So that's something we can get from our DBS data. And we took those Raman spectra at the end of each stage when it's reaching equilibrium. And here the Raman spectra at 0 and 40% RH is a very broad peak showing the amorphous state. And exactly above 60% RH, there are some new peaks showing up here. That indicates of the crystalline state. So this Raman spectra just confirming with our observation in the DBS data that the sample goes through the amorphous to the crystalline phase change at 60% RH. So the whole setup here with the DBS as well as the Raman and the video camera just give us a full idea about these material changes at different humidity. And then we will go through some kind of application with the DBS technique. So we basically have two very typical methods for the DBS measurement. The first one is the step method, just we introduced in the previous slide, that we increase the humidity step by step. So here's an example with the rice starch sample showing the kinetics information about this moisture sorption. So the same here, the blue line is the target partial pressure or relative humidity at each stage, and the red line is the change of mass for the rice starch sample. So at each stage, the sample reaching equilibrium and then jump to the next stage automatically. And it's a two-cycle experiment with both sorption and desorption. And this time, as you can see, the second cycle can go up to the same level as the first cycle and go back at 0% RH at 0% change, mass change. That means this moisture sorption for the rice starch sample is a perfectly reversible process. There is no molecular, like water molecule trapped inside the material at the end of desorption steps. And we can take the mass, equilibrium mass content of the material at each humidity, and then we can plot this mass change, equilibrium mass change, against this target relative humidity. Then we will get this water isotherm for the rice starch moisture sorption desorption. So the red line is for the sorption branch, and the blue line is for the desorption branch. Some kind of information we can get from this water isotherm. For example, at 90% RH, this sample can pick up about 20% change in the mass. That means this sample has very good affinity with water. So the water capacity for the sample is about 20%. And there is a gap between sorption and desorption. This is called the hysteresis gap, and this is because it has very high uptake of the water molecule, and those water molecules are not just on the surface. It will penetrate the surface and go to the bulk of the material. So during the desorption part, when the water molecule desorption from the bulk is a diffusion limited process. So this hysteresis gap, just confirming with this moisture sorption mechanism, is a bulk sorption dominating mechanism. So This is the shape of this isotherm is a quite typical type 2 isotherm, widely found for the food material, which shows a monolayer region to begin with, and then a multiple layer region for lightly bound water, and then free water region at higher humidity conditions. The free water is used for the growth of bacteria, yeast, or mold that will destabilize the material. So we can use this water isotherm to optimize the shelf life or the stability of the food products. So based on the classification, there are different types, 6 types of isotherm. So type 1 isotherm is typical for some macroporous material. Type 2 and type 4 isotherm are typical for the food samples that the water molecule will interact with the surface, forming the monolayer first, and then it will further interact with the first layer to form some multiple layers. And from the type 2 and type 4 isotherm, we can calculate the BET surface area of the material. The type 3 and type 5 isotherm is more like some condensation of the pro molecule on the surface, that the probe-probe interaction is too strong that will form some cluster on the surface rather than cover the whole surface with the monolayer. So we can use the isotherm to predict or to optimize the shelf life conditions. And one of the equations we can use is the Young and Nelson equation, which gives the constant about how much monolayer and multiple layer from the full isotherm. And the other constant gives the idea about the degree of the interaction between the pro molecule and the solid surface. So these are some very useful parameters for the shelf life and stability of the food materials. And the other method we widely use is the ramping method, which is a quicker and much easier way to measure the stability of the solid material. So it's very similar to the DSC temperature ramp. In case of the DVS technique, we will ramp the humidity from 0 to 90% RH at a constant rate. So the blue line here. And here's the result for the lactose sample again. And the red line is the change of mass for the sample. So the sample is losing mass because of the drying stage, just the flow of the carrier gas. And at the very beginning of the humidity, the increase is quite slow. It's due to the surface sorption of the material. And then after a certain point of humidity, the increase of the mass will become dramatically increased. And that's because the water molecule not only on the surface this time, but also penetrate the surface and go to the bulk of the material. So before and after, the change in the middle here is count for the glass transition of the material. And with the slope before and after this change, we can then calculate the glass transition humidity for the sample at certain temperature. And as we keep increasing the humidity, this sample also goes through the crystallization, that the mass will drop dramatically due to the crystalline state has smaller surface area as well as less sorption capacity. So with this single experiment at 25 degrees, we can get first point for the glass transition of the material, and then the second point for the crystallization of the material. And this is the experiment we perform at 5% per hour ramping rate. And if we change in the ramping rate, we can then get a correlation between the ramping rate and the glass transition humidity. And from the intercept of this line, we will then get a critical glass transition humidity at 0% ramping rate. And this is important for the storage of the lactose sample. So above this humidity, the sample will go through the crystallization. The glass transition. And the previous experiment just at certain temperature, 25 degrees. And if we do a series of the ramping experiment at different temperature, then we can get the stability mapping of the metastable material. So at each temperature, we can get 2 points one for the glass transition, the other for the crystallization. So with the increasing of the temperature, we can get a blue line for the glass transition, and then the red line for the crystallization. So from this stability mapping, we can easily to predict at a certain condition of the material, at a certain combination of the temperature and the humidity, the sample is at a stable amorphous state, or the crystalline state, or just unstable state to change the structure at time to time. So this stability mapping is very important or very useful to predict the stability of the material at different conditions. Another ramping experiment we performed with the coffee granule, which we exposed the sample with the humidity ramping first from 0 to 90% RH and then decreased to 40% RH. And we also took some photo image during the sorption and desorption steps. So during the sorption process, you can see up to 60% RH, there is no much difference uptake for the moisture sorption. But after that, there is a sharp increase. At 90% RH, the in situ image also shows the sample already changed the color for the sample at 90% RH compared to 60% RH. And during the desorption step, it keeps increasing mass uptake and then reach maximum at 75% RH. So the deliquescence point is somewhere between 90% RH and 75% RH. And this is a stability mapping for the coffee granule, and we can perform similar experiment for other sample as well to study the stability at different humidity at certain temperature. And another example is the protein-sugar interaction to stabilize the sugar sample, where we have the right line is 100% sucrose sample, and the black line is 100% protein sample, and the other lines for the mixture between different ratios of the protein and the sucrose sample. So where we notice is around 25% RH, all the sucrose containing sample has a goes through the glass transition, and this meets quite well with the literature reported value for the glass transition of sucrose. And then at about 50% RH, for the sucrose 100% sucrose sample, it will crystallize at about 50% RH. But with increasing of the protein concentration, this crystallization point is shifting to the higher humidity range. That means this protein is behaving as the stabilizer that stabilizes the protein-sugar mixtures. This is probably due to the protein-sugar interaction may delay the sugar nucleation that will result in the inhibited crystallization. And all the sucrose containing sample also go to the deliquescence point above maybe 85% RH. So here just shows a very simple XRD with the DBS technique to measure this kind of phase change about sucrose sample. Another parameter we can use for the prediction of shelf life is the heat absorption. So to calculate the heat absorption, we need to do the experiment at least 2 different temperatures. So here we use the fresh and aged meat sample at 25 degrees and 35 degrees. The aged meat sample is the same sample after 1 week time in the fridge, and the fresh sample shows very similar, like almost overlapping of 2 different temperatures. For the aged meat sample, it shows a quite large difference in the uptake at 35 degrees compared to 25 degrees. So from the isotherm, we can calculate the heat absorption with our macros. It's summarized in the table here. So the heat absorption is much higher with the fresh meat sample compared to the aged meat sample. And the heat absorption is also increasing with the increasing of the calories for the fresh meat sample, which indicates the interaction between the water and fresh meat sample is also increasing. Well, for the HME sample, the value is much smaller and it doesn't increase at all. That means it's also close to the heat of evaporation for the water molecule. So in the fact, the pro molecule, in this case is water, is interact with only the other water molecule, resulting in some condensation on the surface rather than interact with the meat sample itself. So that's how we use the heat absorption parameter to predict the behavior of fresh meat and aged meat sample. The last kind of case study is about the diffusion measurement of the packaging material. So the moisture transmission rate is also very important to measure in the food industry. And we do have a special device called pin cell to measure the diffusion rate and the permeability of some thin film sample. So this pin cell is composed of 3 parts. We have the lid of the cell, the cup of the cell, and 2 rubber O-rings to seal the sample in the middle. And the yellow atom here is the thin film sample. So with the pin cell, we can measure the moisture transmission rate, the water activity, as well as the diffusion or the permeability of the thin film sample. So to start the experiment, we will first to put some drying agent inside the cup here, and then we will seal the cup with the film of interest. And we change the outside concentration with our DBS instrument for different concentration. So the vapor molecule will just penetrate the surface from the top to the bottom with one-way direction only. So we can measure the one-way diffusion coefficient as well as the permeability of the film sample. So according to the Fick's law, we have the thickness of the film sample, and we have the mass at equilibrium, and we do the fitting for different humidities, and then we can get the diffusion coefficient of the film sample at certain humidity. And from the slope, we can also calculate the permeability of this thin film sample. So the case study here, we have the diffusion study. Actually, it's a co-diffusion study for the packaging material. Here we use Captain film sample as an example. And we measure the water as well as the methanol diffusion on this film sample at different temperatures. And this methanol just represents a kind of flavor molecule used in the food industry. So it can be any kind of organic vapors. And we designed this method basically in 3 different parts. So the first stage is the methanol only stage, has 50% methanol flowing to the vapor through the film. And then we have the second stage is the water only stage, so 20% water. And the last stage is the combination of 2 components. So we introduce 50% methanol in the presence of 20% water as the background, and we want to study the effect of the background humidity on this methanol diffusion. So we perform the experiment. Actually, I don't have the data here, but we perform the experiment at 2 different temperatures. So what we get from the result is with the methanol only diffusion for the first stage, the diffusion coefficient we calculated is quite similar to each other. So temperature has very little impact on the methanol diffusion in this case. But temperature has a very huge impact on the water diffusion where we calculated for the water only stage. And for the last stage, with the presence of water, the diffusion rate of methanol also improved at higher temperature, where we got from the diffusion rate at 2 different temperatures. So that's how we calculate or measure the temperature factor as well as the background humidity factor on the diffusion rate for the packaging material. And we can also use this pin cell to study the water activity for the material as well by doing a calibration curve with the separated salt sample. And then we can put the sample of interest into the cell, and then we measure the moisture or water activity content inside the food material. So for example, here we get the result for the honey sample, the ketchup sample, as well as some milk powder, and it has really good agreement with the literature reported values. And similarly, we can also put some flavor molecules, some liquid inside the cup by putting, and then seal the cell with the storage bag. Then we can measure the mass loss of this liquid sample to calculate the vapor flux of certain kind of flavor molecules. So I just gave you an idea about how the DVS technique can be applied in the food industries. So we can measure the moisture sorption behavior to determine the shelf life of the material. Or we can also use a combination of the video and also the Raman spectroscopy to get a complete understanding about these material changes at different humidity. So I hope you will find DVS useful in your future research, and I hope it's clear for this presentation. But if you have any questions, just let me know, and thank you very much for listening. Thank you.
Thank you, Mei Shan. That was a great presentation. We have a few questions right off the bat, so just before we go into those, I just wanted to remind the audience that they can either submit the questions in writing in the questions panel, or they can raise their hand to ask the question themselves over the microphone. So the first question we have, Mei Shan, is someone has asked, what is the typical sample size for DVS measurement?
Okay, thank you for the question, John. So basically, we have two different configurations of the balance. So the low mass balance is more accurate, has smaller resolution, so we can put up to 1 gram of the sample. And we also have a high mass balance to put up to 5 gram of the sample. But as you know, we have a really sensitive balance. So if the sample can represent, is very homogeneous sample, can represent the whole part of the sample, we just need to use about 10 to 20 milligram of the sample if the uptake is up to 1% change in the mass. But if the uptake is quite low, just surface sorption, we might need to increase the sample mass up to 100 milligram to get a good noise to signal ratio. The more the sample you use, the longer the equilibrium time it will take. So we typically just use the optimized amount to get a quicker experiment done.
Brilliant, thank you. Another question will come in here, and they ask, is it possible with the modular accessories to use the camera and the Raman at the same time?
Okay, thank you for the question. Yes, I think maybe in the previous slide I showed a stand. So the camera will go to the same location as the preheater, is in the bottom of the sample chamber. And the Raman, there will be a simple port on the top of the sample chamber. So we can basically use the Raman gun as well as the photo image at the same time during the experiment. But the camera and the preheater will share the same location, cannot be used at the same time.
Great, thank you. We'll just wait a moment or two for any other questions to come in. I don't think there's any other questions coming, Mei Shan, so we may wrap up for there today. Before we wrap up for the day, is there anything else you'd like to add for the audience?
Yes, so basically, actually, we have lots of different application notes for the food applications. It's in much details compared to this presentation. So if you're interested in any slide or any applications, you are welcome to contact us, and we can send you the application note, or we can go through some specific application based on your product in details. And if you want, we can also share this presentation after the meeting with you.
Brilliant. Thank you so much, Mei Shan. And thank you as well to all of our audience for attending today. We have other webinar and educational content coming up. Our next webinar would be exploring moisture content and pharmaceutical ingredients. That's taking place on Thursday, the 9th of September. And of course, we have our headline event, the Sorption Science Symposium 2021 online, taking place at the end of September. This is a fantastic event that's going to be offering a full dedicated absorption science agenda, populated by some of the leading experts from around the world, and it will explore a range of topics across both IGC and DBS, with a range of industrial applications being discussed. So I strongly recommend you go to our website and check out the agenda, and get your ticket today. There will also be some fantastic networking opportunities to reconnect with the global audience and make some new connections, some new research partners, and catch up with some old peers and colleagues. So if you'd like more information about our upcoming webinars or the Absorption Symposium, please go to www.surfacemeasurementsystems.com/webinars. Thank you all again for attending today, and we hope to see you soon. Thank you.